fill in parts of the industry that just are not all that clear, right? So we help out in the building automation industry, and we make sure that you guys have what you need when you're designing and specifying building automation systems. So we went through BAS 101 with Emily, and it was a lot better, a lot deeper than you probably expected for a 101. And I really like that session, because if you're not familiar with building automation systems, now you know what the benefits, now you know the capabilities, things you have to consider. The specifics really start with 102, and if you're going to stick along with 103 and 104, we're going to run you through everything you need to consider when you're designing a building automation system. So, once again, if you don't know already, the reason we're able to provide you guys with continuing education credits, Delta Controls, we're registered with the American Institute of Architects to provide you guys with these credits. And will the slide decks be sent out after the call? I think I can make that happen. That's fine. I can PDF it. So for questions during the presentation, feel free to unmute yourself and interrupt, but keep the questions, at least for purposes of this, manufacturer agnostic, product agnostic, for purposes of AIA. If you have any questions, company questions, keep those for after. But any questions about what we're talking about here today, feel free to unmute and interrupt at any time. And all this material is copyrighted as of 2024. So quick agenda. We're going to look at the fundamentals of building automation systems. We're going to look at hierarchy basics, what makes up a building automation system, right? Top-down view architecture. We're going to look at how to approach a control schematic. We're going to look at a mechanical schematic that engineers usually design. They'll also put next to that a sequence of operations or a spec, and we're gonna look at how we're gonna approach it from the views of an engineer, from the views of a mechanical estimator or controls estimator. We're gonna look at a couple of typical points, and then we're gonna jump into some protocols, ways for devices to communicate in the building automation system. And then we're gonna look at the required devices, right, for a BAS network, right? All right, so this is in a nutshell what BAS 101 encompasses. All right, what Emily was talking about, and this is kind of, we're breaking down the components here, right? What makes up a BAS system? Looking at this graphic, and we're not going to spend too much time on it, but just to get everyone speaking the same language, it's top down. The top level, get my laser pointer. Top level here is what we refer to as management level or enterprise level, right? Management is more commonly used if it's a single building, right? And it includes a more central hub that can oversee the entire building. And that's on this enterprise level. It'll often include a graphical interface for monitoring and control, which will allow operators to interact with the entire building automation system. If you have multiple buildings or campuses, that's when you're branching into the enterprise level of things, right? In a larger system, you may have an enterprise level that can connect multiple sites to view centralized data across all buildings. You can also include cloud computing on this level. Modern building automation system implementations will integrate cloud services for advanced analytics, remote monitoring, and scalability. Next up is your supervisory building control level. And these servers, these heavy controllers, right? They coordinate multiple controllers and systems. They may handle tasks like scheduling, alarm management, and data logging. And then as you go down, these are more application-specific controllers, but depending on the size, you may still need to use a more supervisory controller, depending on the manufacturer's product line. And these devices receive data from sensors, right, that live down here. They receive data, process it, send the commands to output devices, open a valve, turn up the cooling in the building, and then but the whole point of it being application specific is they manage specific functions like HVAC, lighting, or security. The field level, which is not really pictured here, but that's where the sensors, the inputs and outputs, all different actuators laid out all over the building. Those are the devices that directly interact with the building's environment, right? They collect data, temperature, humidity. Sorry, somebody said something. Okay. So sensors collect data, temperature, humidity, occupancy, and the actuators. And then basically that all reads back to these controllers and fills the building automation system with what to do, whether they're just going to be trended or actual outputs to the building to enhance occupant comfort. For BAS point control, there is a distinction that I want to make between control, and the next slide will be monitoring. And the whole point of control is to influence the operation of the system, right? Those sensors on the last slide, they pull in data. Now you may want to turn on the thermostat if the room is hot. The room being hot is just the input, right? And that's the monitoring part. The control portion is converting that to an action or output, right? So the room is hot. What do you want to do? You want to turn up the air handling unit. You want to increase the cooling throughout the building, right? And I like to bring up this slide because while we can have these physical and hardwired points, it's also important to note that upfront, as you're designing the system, some of these can now be put into a virtual world. You might have app integration or automatic points. So it's good to know about that upfront and your options, when designing your system with the owner. BAS point monitoring versus actually converting an output into space. You're observing and recording data, right? Say you own the building and want to check energy levels, trend analysis. All this is sensing and pulling in data, right? Think of tax credits, LEED and WELL, which Emily again mentioned in BAS 101. Those are all things and standards that are out there that they rely heavily, and a big portion of it is just pulling in the data and figuring out what to do with it, right? More and more governing bodies and rules, and then on this side, there's also a huge cost savings when it comes to trending, optimizing peak hour usage, things like that. Again, when it comes to monitoring, this is crucial in designing a front end, right? That can accomplish what your client is after. Do they want on-the-go cloud-based, or do they want an HMI, which is an actual interface to interact with physically, or do they want who do they want to have access in the building? What kind of trending and logging capabilities do they need? Will they need historian capabilities? All of this should be kept in mind when you're designing the system up front and choosing an appropriate way to monitor everything that encompasses the system. And this can help to prevent all the change orders and retrofits in the long run. Here's a lot of common points. We're not going to go through all of these, but a huge highlight would be number 5, right? Again, we mentioned LEED and WELL, and we're seeing this talked about heavily in our industry in both ASHRAE and other governing bodies. So when you start discussing common points your end user wants to measure, go ahead and bring this one up and make sure you're planning ahead for this. CO2 and indoor air quality points, right? Here are other points to be familiar with, and remember that a building automation system does not stop at HVAC. We now have different types of specifications or sequences of operation. You have a Division 23 or a Division 25. Division 25 is your integrated building, and it doesn't just stop at HVAC. You have security, lighting, and other access control, different things that come together and to automate your entire building. So keep that in mind. Okay, so we keep saying BAS points, and we looked at what that means in the physical world. But as we dive deeper into the control or digital world, that's just when an input or an output is represented digitally, right? That's what you're looking at here on the screen. And it's referred to as a BAS point. In the digital world, every point has a name and an address, right? The address is a number that defines where in the database the data will reside. So all of those common points that we mentioned, if they're being controlled, this is what you'll see from the digital world of things. This is what actually lives inside the program of the controller. Within that, we have a couple of different things to focus on. The first thing is point types, right? A couple of different types here. You have both real and virtual. And within that, inputs and outputs, right, of both can be analog and digital, and we'll break all that down. But we're just showing you here what's happening under the hood of the controller, right? When a signal is wired to a controller, it has to pass through what is called an analog to digital converter. Simply put, this is an electronic device that takes a signal and converts it to something a microprocessor, which is inside this controller, can understand. You may have seen specifications calling for 10-bit or 13-bit or 16-bit inputs. That's specification for the A to D converter. 10-bit is less precise and 16-bit is more precise. For those that are actually interested, it's calculated exponentially such that 16-bit is 64 times more precise than 10-bit. These are things that can be specified, and they have been in the past. It depends on how deep you are into the controls world and how much you want to specify where you want to get into those details. Same with outputs, right? When a microprocessor or digital controller wants to output a signal to a valve or actuator or relay, the signal is converted to an electronic signal that the field device will understand, right? So back to the different types of points, hardwired or real points, and then you have software and virtual points. Hardwired or real points are those points that have an external device, right, that is inputting a signal or that is committed by the controller. So there's an actual wire, there's actual power happening, a transfer between them, data moving between the device and the controller. When we speak about the inputs and outputs on a controller, we're talking about the real points. The more inputs and outputs devices in the system, the more real points you'll have. So you need a controller with higher input and output counts, right? And these are some things that Emily will take you into consideration with BAS 103, right? As she dives through systems and boilers, chillers, cooling towers, different types of controllers can manage certain types of systems depending on the size. And that's something I also mentioned on the architectural level, right? You have supervisory and application specific. So the larger the system, the larger or the more demand of a larger controller. So every device that's read or monitored or controlled by a controller is turned into a real point. For example, temperature sensors, current sensors, meter, pulse inputs, and valves. Software or virtual points are those points that are not tied to a real device, but still are needed to make the program work. For instance, time delay. Time delay is a virtual point, right? There isn't a physical device that comes back to the controller that brings in something called time delay. It exists in the program with a real name and address, but it does not connect to any real device. In a BAS program, there could be dozens of virtual points that the programmer uses to represent set points, time delays, statuses, conditions, intermediate signals, etc. These points take programming time, but they don't actually require an input or output at the terminal of the control. Wiring of the device is not necessary. There is no actual physical presence to it. Here's a trick question, and you can unmute if you know the answer. Is room set point a real or a virtual point? Room set point. That could be for temperature or humidity, it doesn't matter. Set point. Is that a real or a virtual point? So unmute. Okay, I see virtual. Okay, I see 3 answers for virtual. It's a trick question, by the way, but okay, virtual. All right. All right, that's that to some level, yes. Okay, so the answer is it could be either. If the room sensor is only a sensor out in the field, and the set point is only adjustable from the building automation system, then it's virtual, right? But if it's adjustable at the thermostat, then it's a real point as well, because the thermostat has an electric signal, right? That you can toggle the thermostat on physically, right? And then it comes back to the controller. But here's the thing: you can also program it in the building automation system, as well as it being a physical device with the thermostat, right? So it could be both. However, slider is real. The actual point is virtual. However, slider is real. Yes. So looking at it, yes, it can be either. Thomas, correct. Yep. Thomas got it here. Okay. I wonder if I talked first or he answered. Just joking, but yeah. So the answer is it can be both, depending on how it sits in the field. That's what it really relies on. A thermostat will mean that you can actually toggle the change in real time, or it can be done in the program. Okay. Now to inputs. When it comes to an input versus an input again. This is where monitoring, right, takes place. This is you're pulling in data, right? And that's split between analog and digital, whether inputs or outputs. The analog side, it provides continuous but proportional data, right? Temperature is proportional. That's why it's analog, right? So it's calibrated via voltage, right? It could be calibrated to a specific electric signal, and depending on the range of temperature that you expect your system to experience, you're going to calibrate that voltage to that range, right? So that's why that would be analog with temperature. A digital would be turning on or off your light switch, right? So turning on the light, it has an on, right, status, really ones and zeros, on and off. That's what it does with digital. And again, these are just inputs, right? So turning on the light isn't actually an input, but the system finding out that or realizing the status of the light being on or off, that's where it's an actual input, right? So the system is reading the data. So when you think of inputs, think of sensors, right? Not necessarily a valve opening or a temperature or an air handling unit ramping up the VFD speed. You're thinking of just sensors collecting data and being read at the building automation level. So for outputs, now you're changing things in the field. You're changing things in the space. You're controlling the speed of a valve. You're changing the position of a device, or again, you are actually turning on the light, right? Turning on the light is an actual output, right? You're changing something in the space. And again, analog or digital. This also works. The proportional side from analog works also for valves, right? Depending on how much you want the valve to open up, that'll also be calibrated to an electric signal, right? So you'll calibrate it based on 0 to 100, 0 to 10 volts. Depending on that, you will calibrate the valve, and depending on what you want the valve, what position you want the valve to be, that voltage will be read at the controller level. So, and then digital output, again, opening and closing light switch, deciding to open up the valve. That's also a DO, right? Open the valve, and then you can control it proportionally through an analog output. Here's a BAS schematic. Here's some field devices laid out on some ductwork. We talked about inputs and outputs. We're just going to look at a couple of points here, and I'm going to ask a couple of more trick questions. Just an example here, you have supply pressure sensor, right? Notice it doesn't say sensor, but I know that because it's an AI, right? So it's not a switch. And I'll mention the distinction in a moment, but AI, so this is reading the actual pressure value, duct pressure value in this duct. So that's why it's an AI, right? From a controls contractor perspective or an estimator, I'm looking at these points and I'm collecting information, right? So I have one AI, I have one DI, I'm just counting them up, and I can put a price to this efficiently, right? And I, as a designer, well, the designer should be creating this schematic in the first place, but some tend to not create schematics as detailed as this, right? With AI, DI. And when you don't, you leave out information, right? You also leave some confusion to the controls contractor versus the Division 26 base electrician versus the equipment manufacturer. So the more detailed this is, the better price, the more accurate the job will be done. So a couple more examples. You have another analog input here, supply temperature sensor. And again, this is reading the actual value of the supply temperature in the duct. I have a question here, right? And this is talking about static pressure, high static pressure. Why is this a DI and not an AI? And this is probably not going to want to be typed. Does anyone want to explain this? Unmute yourself. Why is this a DI and not an AI? Why is this digital or binary versus an analog? Because we're talking about pressure, right? And pressure is not just on or off. So why is this a DI versus an safety circuit interlock to the VFD? You want to elaborate that on Mike? All right, we just want to know if it trips so we can shut down the supply fan. Exactly. So meaning, if you guys are looking at the chat, so what he means is we don't care about the actual value of the static pressure in this space. It's a high static pressure switch, right? We want to know if it trips, right? We want to know if that value, which we've calibrated, we know that value that we don't want to surpass. So we're going to set this high static pressure switch to that value. And if the pressure in the duct surpasses it or hits that, it's going to trigger the switch. And that's all we know, right? Maybe later on, if the pressure reaches this value, you can get the actual value, right? Because this is a supply pressure sensor, so it's going to collect the actual value. But over here, we don't care. We just want to know if it's triggered. And that's why it's digital, right? On, off. Did it trigger or did it not trigger? That's the difference between digital and pulling in the actual value via analog. You have other things here like a mixed temperature sensor. You have a low temperature sensor. We're going to talk about that on the next slide. This is also talking about temperature, but it's DI, and we'll get straight to that here, and we'll mention why it's a DI versus an AI. So safeties are also to be considered when you're designing your building automation system, when you're designing your schematic, as you lay out your devices and sensors with the equipment along the space. In addition to the sequence of operations, you're going to see devices like these and things like the high static pressure switch on the last slide, right? Why is it a DI versus an AI? Well, we need to know if it was triggered. That's for safety reasons, right? We don't want to blow up the ductwork with high pressure, right? So that's kind of what the high static pressure switch looks like. Is there that much of a savings by using a switch over a sensor to make it seems to allow more flexibility and data? The short answer, Kerry, is that it depends on, well, in this case, it's a safety thing. So you want to know early, right? You want to know early on if the pressure is really high. Having a supply pressure sensor here in this space, I'm pointing, but you guys don't actually see me. Here's my laser. Second. Yeah, so having the supply pressure sensor here may need it in part of the design, but having the high static pressure here is necessary to prevent any issues, right? So you may have to have both. So it's not picking one or the other. Again, it comes down to design, as you're designing the building. And as a consultant, you should be consulting your owner. You need this for safety. You also need that to continue controlling the rest of the building or things throughout the ductwork. So I wouldn't say that one is needed over the other. And I wouldn't also call this a redundancy. I think both are necessary. So that's what the high static pressure switch looks like. Here's another safety consideration when you're designing this schematic, a free stat, right? Now it's called a low temperature sensor. And again, another question, why is it a DI versus an AI? We're still talking about temperature. Are we pulling in value here, or do we just want to know if this certain temperature that we calibrated is surpassed, right? Or is it that low? And why is there a low temperature sensor here, right? For what purposes? You have a cooling coil here, right? You have also some heating happening here. So you don't want this cooling coil to freeze, right? If the outside air temperature is really low, you probably want to close this outside air damper, right? And start use mechanical cooling or heating within the space to prevent the temperature dropping too low and hurting this cooling coil, right? You can freeze the cooling coil. You can have a lot of damage, a lot of issues. So this free stat or low temperature switch is set here for that purpose. So we're looking at a BAS points list here, the purposes of a points list can be called a responsibility matrix or a points list. And again, if a consulting engineer decided to put this on a plan and spec, that's, they're already ahead of everyone else because not every consultant tends to do this. And the reason for this is to lay out the points of the system, right? All the stuff we see on the ductwork or in the schematic can be laid out here, right? Depending on what it is in the, is it a hard point? Is it a hardwired point? Is it a virtual point? So virtual is not shown here, but it can be shown afterwards on the column. It can be laid out. Can you please mute yourself? Okay. All right. So so when you lay out the points, it becomes easy for the person to pricing it to know what they're responsible for, to know what they're responsible to wire, and to get a nice budget going for this project, right? Because before this even hits the street, if you have something like this laid out, if you are engaged in talks with specific manufacturers and you have a per point cost, like some budgeted cost to every point that those contractors are going to provide you, you can provide an early price to your owner or to your building owner or customer and tell them, listen, the project will cost in this range, right? So this way, when the actual price hits the street, it's not a surprise and you have a specific range and you can tell people, listen, you're too low, you're too high. Now we're going to look at some, control logic, right? How does a controller actually process information? And what does that look like from metaphorically to a human, right? So when you see an input, also a LTDT reacts to stratification input, where the main sensor is an averaging sensor. Low temperature. Thomas, is that low temperature? Is that what you're saying in the chat?
Yes.
That thought. Okay,
Yes.
low temperature. Okay.
Yeah, it reacts to a small area of cold air, so that you prevent stratification from freezing a coil.
Correct.
As opposed to an averaging sensor, you could have a great average sensing, averaging. You could have a great average temperature, but still have stratification.
Correct. Does that go back to carry where it's like use one or the other or use both? Yeah, I mean, it comes down to how you're designing the system, right? There's safeties and then there's necessary things we need to control the equipment or valves or whatever downfield.
So, absolutely, on a low temp detector, absolutely, yes. They do two different jobs, yeah.
Perfect. Thank you, Thomas. Okay, so how does a human sense, right, change in the space, and how does he react to it versus a controller? And that's kind of the whole point of this, right? So I'm in a room and the temperature is hot. That's my input, right? I realize the temperature is hot. Okay, I'm processing that information. What do I want to do about that? Well, maybe I want to go and toggle the thermostat, right? So same thing, the controller does the same exact thing. Gets an input through a sensor out in the field, temperature sensor. Let's call it a thermostat because we're going to want to do an output, or for controller purposes, it can also be programmed in the system, in the controller, to change the temperature. So it pulls in data through the sensor, processes through whatever horsepower is in this thing under the hood, and then you have an output, right? It's hot, and there it is. There's the example. So the temperature rises, and you get a point generated. Right? There's a name and address to that point, and that's pre-programmed, right, prior to project delivery. And then you have this code here. This is actually what it looks like, what the logic is going into the controller. If the thermostat is on, then on, which means turn on the fan. Else off, else keep the fan on, right? So the thermostat is on, right, because the temperature went up. It can do that automatically, or someone went and toggled the thermostat to turn on. And then this point hits the controller, and the controller sends a digital output. Let's turn on that fan, right? And then it sends, there you go. The relay closes and allows power to flow. Then you have your air handling unit or supply fan turning on and pushing cool air throughout the building. That was an example of a digital point, right? So turn on the fan. That was the output here. In this case, we're going to look at an analog point, right? So again, the temperature is increased. You have an analog input. The temperature is sensed to be high. Here is your code that's going to go into the controller. If the temperature sense is larger than 75, then turn the valve position to 100, right? I don't think you really need 100, but in this case, we're going to turn off the valve all the way. Else, if the temperature sensor is less than 72, then keep the valve closed. Then valve position is 0. Else, valve position is a whole code that's going to be, that's going to be there for the rest of the program, the rest of the building, just to measure what's going on in the space. So anyway, so the temperature is sensed to be high, hits the controller, and the controller says, let's open that valve, right? So let's open the valve is not actually an analog input, but in this case, we're going to do something different, right? So we skip that, right? So we turned on the valve, that's a binary, right? So turn on the valve is binary or digital. Now controlling the valve position or valve position, that's where the analog output happens, right? And that's what's shown here. So again, the temperature is high. Now the valve position is ranging between 0 to 100, depending on the voltage that's sensed, right? Now this can be calibrated to temperature, right? So this is what's calibrated, right, to temperature. Now we have a range of temperature you don't want to surpass, you don't want to go below. So that's what you're going to calibrate this to. And then depending on that, the valve will open and close proportionally. This is why it's an analog point. All right, we're going to talk about closed and open loops. It's important to understand the difference between them. And a closed loop is where the sensor is actually that's doing the sensing will actually see the action taken by the output, right? Sounds like a lot of BS. For example, in the top right, when a sensor calls for hot water valve to open, the sensor, the supplier sensor, says, "Listen, it's we need some heating in the space," right? So it says, "Hey, turn on, open that hot water valve." And it allows water to flow, and then you get heating, you get more conditioned air to flow through. That same sensor will sense the change, right? This is why it's a closed loop, right? Because this will keep telling the controller whether to open or close that valve, right? Proportionally. That's why it's a closed loop, right? An open control loop is where the device that drove the input does not actually see the results, right? Or doesn't actually adjust based on the results. Now, an example of this can be outdoor reset, right? The input is the weather or the outdoor air temperature sensor, which is not here, but this is just kind of like a control loop. Anyways, so the output is the high boiler water set point, right? So the boiler is going to supply hot water. As the boiler water temperature goes up, the outdoor temperature sensor is not actually going to change because it's there for one reason, to sense the outdoor air temperature, right? Outside air temperature. So that's an open loop. And in almost all control loops that are used in most manufacturers and most control scenarios, they're all going to be closed, right? Like this scenario here. It's very hardly an instance where, open control loops are actually used. Except maybe in this outdoor air reset example. So those are the fundamentals. If anyone has any questions, I can pause here for a minute and we'll go right into protocols. There's not much longer left for the presentation, so we do have some time if you have any questions. Keep going. All right, I'm going to keep going here. Protocols, this is how two devices will communicate with each other, or the whole network really. Think of it as different languages to transmit data, and it's important to know common ones that are in the space, and specifically ones that you should be really focusing on and specifying as well. So there are different BAS protocols. The first one here is BACnet, right? And it's in the name, Building Automation and Control Network. This is an ASHRAE standard, ASHRAE 135. It is not a proprietary creation. This is something open to all manufacturers. This is the most common one used in the building automation industry. And you should definitely be specifying in BACnet, if not BACnet Secure Connect, which we'll get to in a moment. So that's BACnet Secure Connect is actually an encrypted form of BACnet. The ASHRAE committee decided, hey, why don't we not reinvent the wheel to encrypt data? Let's just use how the internet works. And I'll talk about that in a moment. And actually, today we're presenting on BACnet Secure Connect. If you want to see how this technology actually takes place, you'll feel better about it. You can tell your IT department to back off. Jesse's on this call. He likes it as well. But this technology actually works. If you have a system that's deploying BACnet Secure Connect, you have so many capabilities that open up, like remote monitoring, cloud monitoring, things like that. You also have Modbus. This is another common protocol, but it was really made for the industrial automation industry. But again, you may still see these on some boilers, some equipment manufacturers that still use Modbus to communicate. But again, really just focus on these two. We'll talk about MSTP, IP, different layers that the language can speak in. You also have LonWorks. This is also used for automation and control networks. Again, not very common anymore, right? If you have LonWorks, you're using a pretty much outdated system. You should, again, still specify BACnet or BACnet Secure Connect. DALI is a lighting protocol. Be familiar with that if you're into Division 25 integrated buildings, because you're going to want to specify, right, the latest DALI standards. Inocean is a wireless standard, right? This is used for between so many different devices, and it uses very low energy, right, to communicate between the devices. MQTT is a IoT standard. It's also for wireless, and this is how you kind of integrate apps into your building automation system. And again, it's heavily used nowadays, and you can do a lot of stuff with it. You can use third-party APIs and integrate a lot of stuff to your BAS. So again, the focus of this, we're not going to dive into this, but the focus of this is you should be looking at BACnet or BACnet Secure Connect on top of that. So different ways that BACnet or Modbus or all of them can communicate. So it can communicate through IP, right? This is different layers, different speeds, depending on the wiring, depending on the wire you're using, and the capabilities of the controller. Because you could have an IP-based controller, or you could have an MSTP only controller, right? MSTP is a lower speed protocol. That's usually seen on the VAV level. IP is, this goes all the way up to your server, and this uses high speed, right? Your IP stands for Internet Protocol. You're using the internet to transfer the data. This is efficient when it comes to wiring, right? You don't have as much wire as Ethernet. Ethernet has really high speed, but you have wires running all over the place, and this is not where you go wireless. And with Ethernet, you're not really able to do the cloud monitoring or remote into your building. Now, specifically IP and Ethernet, I want to show some distinctions here, and I really kind of mentioned some of them. So IP works for both wired and wireless networks, right? Versus Ethernet is typically used for wired networks. And you need cable, you need a lot of wiring for Ethernet. The addressing for IP, you're using IP addresses. For Ethernet, you're using MAC addresses. If you're in the programming space, or if you are familiar with how these building automation systems are set up, then you know that how each device is addressed. Routing may be necessary between different subnets or segments for IP. And for Ethernet, you're not jumping between too many networks. Usually this is for, one physical network that you're wiring up. for interoperability. With IP, you have a lot more interoperability, right? You're connected to other IP-based systems, and again, you can be transmitting data over the internet. Ethernet is very limited, as again, you're talking about a fully wired network. So you're staying on a huge, building, maybe a huge campus, but in that building, whatever's wired up is actually what's communicating with each other, not really externally. Security measures can be implemented for both, but on the IP, now that we're here, that's how BACnet Secure Connect communicates. It only communicates on the IP level. It doesn't go to MSTP, it doesn't go to Ethernet. And here's BACnet Secure Connect. So again, it's an addendum to ASHRAE 135, the BACnet standards. And it's a standardized network security solution, and it uses the TLS security protocol for the common internet security protocol. Don't need to know what that is. The first highlight of BACnet Secure Connect is it adds encryption to native BACnet. What this encryption portion means is you have two devices, and as data is moving between those two devices, the data is encrypted, right? If for whatever reason that data is captured, that traffic moving between them is captured, it's gibberish, it's encrypted, right? You can't really do anything with it. And now that data can hold some mission critical information, and can hold some healthcare patient info, I don't know, depending on the site. But again, it's gibberish, it's encrypted to the hacker outside, which again, you can't really join a BACnet Secure Connect network as a hacker. And part of that is because you have to be authenticated to join in the first place, right? Those two devices didn't just end up, find each other through an open IP port. You have to be authenticated to join the network. And I talk about this later on in today's presentation for BACnet Secure Connect. But the way this works is there's a certificate exchange, and it's done internally by the controls contractor, at least recommended. They use a private certificate authority. They say, I allow this device to join the network, and I allow this device to join the network. Anyone else from outside, do not share any data with them. That's how the authentication process works. And I'm not gonna, dive into this, but it uses HTTPS. You're putting BACnet IP communication or data in HTTPS using WebSockets. Essentially, again, ASHRAE did not reinvent the wheel. They just said, hey, information is moving through the internet. We do mobile banking already. That's secure. Why not just take BACnet data and put it through the internet using the WebSocket method, which allows that two-way communication between a hub and a node without any firewall exceptions. And it's an additional medium to route traffic, right? So meaning you don't have to re-engineer your entire network to get BACnet Secure Connect going on your system. You can simply add two devices that are BACnet Secure Connect capable. And now that traffic moving between them is encrypted. And maybe that's where you want to encrypt, right? Maybe that's where you put all your sensitive data. So again, this is an add-on to existing buildings and networks. And I mentioned this before, but it's not proprietary. So it's open to everyone. And as a recommendation, you should be looking, as a specifier, to specify manufacturers or products that are using BACnet Secure Connect. You should be moving away from those that I guess they just don't want to advance, that don't want to move along with the industry, looking at standards, especially when it comes to safety as well. So if you want to know more about this or exactly how that certificate key exchange takes place between two devices, stick along. I think this is happening around 3 o'clock, 4 o'clock. I'm not sure. But we'll show the schedule afterwards. You can see the timing. PoE is another protocol that devices use to communicate. And this is actually a really interesting one because it's called PoE, Power over Ethernet. It delivers electrical power and your communication through the same cabling. Right. So you're using the Cat5, Cat6 network cables. And because you don't need to run any separate electrical wiring, you're saving a ton of money. Right? You got your electrical and communication running through the same cabling. That saves you money and a riser. If an electrician's creating your conduit or riser for you throughout the building, you just have to run two separate conduits, two separate risers. It's also flexible, especially for remote applications, since you don't require a nearby electrical outlet. These and other benefits have led to a sharp increase in PoE's popularity. Now, except, obviously the limiting factor has been power, right? Can the grid handle all these buildings, turning to PoE? That's really the question for the future, especially with local law 97 and things like that. So the way it works is simple. Ethernet cable that meets the Cat-X standard. It consists of 4 twisted pairs of cable. Now, PoE sends power over these pairs, the PoE-enabled devices. The first PoE standards use the first 2 twisted pairs to transmit data and the other 2 to transmit power. Now, with the newer PoE standards, power and data are both sent all the 4 twisted pairs. And when the same pairs are used for both power and data, the power and data transmissions don't interfere with each other. If you're thinking about that, that's because electricity and data are transported at opposite ends of the frequency spectrum. Electricity has a low frequency of 60 hertz or less, and data transmissions have frequencies that can range from 10 million to 100 million hertz. This is not for power over Ethernet. That's a glitch on my end. So this is just different ways that you can wire things in a building automation system. And depending on, this will depend on, again, your budget. It will depend on what you're trying to do. And again, so starting with the star topology, this configuration will connect each device directly to a central hub, and that's going to provide reliable communication and easy troubleshooting. But it's less resilient, as the hub here, right, will serve as a single point of failure. That goes down, everything else goes down. The ring topology is a different way of wiring, right? All the devices are connected in a circular arrangement, and that offers redundancy, right? Since data can flow in two directions, right? This way and that way. And although it enhances like the fault tolerance where, you have you have more points of failure, any break in the ring is going to reduce the network performance, right? One device goes offline, it's not really the most efficient way. Mesh topology is the most efficient way of doing it. And in this setup, devices connect to multiple other devices. That's going to offer your maximum reliability and resilience, as the data has multiple paths. However, it is more complex and costly to implement. That's why I mentioned budget, right? So when it comes to scalability, right, your network topology, particularly star and mesh, are going to influence your system growth. The mesh is going to provide your most scalability, allowing for easy addition of devices in the future. That's, and that's going to minimally impact your existing network. And then you have redundancy, right, to prevent failure with the mesh. We talked about a lot of protocols. We talked about sensors, controllers, devices, different layers, supervisory, application specific. Here's a sample network layout using the different protocols, the different data link layers. You have Ethernet, MSTP, LinkNet, a wireless standard here. Zigbee is another wireless standard, should know of. This is kind of how it's laid out. With pink being your MSTP, pink being LinkNet. Red is your MSTP, and again, this is a VAV controller, right? And then moving all the way up to blue, which in this case they're using Ethernet, right? They wanted the maximum, speeds for data flow. So as you go up, you're getting more supervisory, higher speeds, more data is happening, more processes are taking place, scheduling and et cetera. And then you even have a thermostat here or sensor that's connected wirelessly. So this is after you've built your system and you've laid it out. This is called a kind of like a riser, right? And again, having this in a control schematic or a set of mechanical plans, it's not likely to see this in every mechanical plan, but if you're thinking of your project and you're building it this way architecturally, again, this is easier for you and easier for the control contractor to price as well. So they know what's required, what the system actually looks like at the end. The final section here, we're going to talk about the network and some network devices that you need additionally to controllers and additionally to the rest of the system. So different network components, we talked about controllers and different types, and we're going to talk about that a little bit more specifically, but Emily is really going to be the one showing you how to select, right, a different type of controller depending on a different type of system in BAS 103. We're going to look at routers, switches, and gateways here. Here's your different types of controllers. So you need servers, right, before you design your network, right? And a server in a BAS, it acts as a central data repository. It stores and processes information for efficient system management, right? Your network switches enable communication between BAS devices, and they facilitate fast and reliable data transfer within a network. Gateways, they bridge different communication protocols, right? Modbus to BACnet or vice versa, right? And again, because not everyone in the industry is standardized on what to use, you still need gateways as you're designing your systems. Routers, they manage data traffic between various network segments, and they ensure efficient and secure communication across the entire building automation network. Here you have the switches, right? Again, this is responsible for connecting multiple computers and parts of the network with each other. This really, will connect you to connect different LANs and allow devices to communicate over the network, right? You can connect computers, printers, servers to the same network switch and route data between them. You have different types of switches, right? Managed and unmanaged switches. The essential difference is the capability to configure the operation of a managed switch, to customize and optimize network traffic for specific applications. Think of an unmanaged switch as a dumb little networking box. You plug things in, they're all connected to one another. You put the switch somewhere and forget about it forever. It requires no updates, no input from you. And really, it's a simple job. Managed switch is a little different, and it does all what an unmanaged switch can do, but you can also log into it via a web-based UI or app to tweak a number of settings. You can enable features and update it with firmware to fix issues. You can add more functionalities, and bandwidth limits, things like that. So, routers are, again, devices that connect two or more packet switch networks, right, or sub networks, right? You can also route here between an MSTP network and up to an IP network, right? Different speeds, different layers. So you're still going to need these on as you design your building automation system. Gateways, again, as I mentioned, they translate between different protocols. Again, understand that the gateways aren't really just human programmed. They're you still have to do it yourself. You have to program these yourself. And they also actually allow different networks besides just your Modbus and BACnet to communicate with each other. So you can, if you're familiar with Tritium, right, or Tritium-based solutions, there's different gateways that translate or move devices, move data between one system and the next. Some distinctions between controller types, right, which we mentioned earlier: building level controllers, more supervisory, application controllers. So again, this is just showing you guys again. One is focused on just I/O capability, right, and that specific function or system, like a fan call unit, and another has some I/O capability depending on the size, depending on what you need, but really acts as a traffic cop, right? It routes data between different devices. It acts also as it can act also as a server. A lot of the programming happens on these levels, and the sequencing as well. Last but not least, and this is kind of a segue into the next presentation, which Jesse will take us away, cybersecurity. And it's extremely important. Part of that is really, as we talked about BACnet Secure Connect, which is, again, an encrypted extension to traditional BACnet IP communication. It's important to consider cybersecurity, and Emily also mentioned this, and we'll keep talking about it because it's not, the last thing that we talk about when we talk about building automation system. When you have mission critical systems like a data center, when you have things like a hospital or a government facility, this is probably the first thing that's going to be considered when designing your building automation system. So you're looking at preventing cyber threats, outside hackers, people getting into your system, making sure that all the communication between devices, allowing only the specific devices you allowed onto the network in the first place, and overall just future-proofing the building automation system. Because as we think of this, outside threats or hackers are also figuring out ways to get into your system in the future. Maybe now they can't because of BACnet Secure Connect, but maybe they're thinking of ways. That's why we have to stay up to date on the latest cybersecurity standards as you secure your building automation network. Jesse will get a lot deeper into that and show you what the latest standards look like in the space. That's all for me, folks. Any questions? That means I did an amazing job. Thank you, man. All right, if you're going to stick along for cybersecurity, I think we're going to get started. I missed a little first. Yes, we are recording. Please check.
Yeah, we'll be recording all
Yes.
of these and sending out the presentations in some way, shape, or form. We were supposed to have a WebEx survey that went to you guys afterwards. So most likely what we'll do is I'll just gather all of the accepted from that WebEx invite, and I'll just send something to you guys with a link to the presentations as well as the recordings. Perfect. And then, like we said, the next one that we will be doing is cybersecurity here just shortly with our resident expert, Jesse. So come back and join us here in about the next 15, actually about 20 minutes. We have a little bit longer. We'll start back up at 1:30.
Awesome. Just bought you guys some time. Thank you, everyone.